how did that go back to that size? That just... Okay, I think we're good now. Okay, so back, sorry about that, but so what are we looking at here? We've got these tensile forces that we're dealing with here. Again, we talked about tension before. If it's tension, it's pulling away from the object, right? In a minute, we're going to see compression. It'll be pushing back towards the piece. Tension is trying to pull the thing apart. It should elongate it. Compression won't do that well. It'll make it shorter, okay, until it fails. That's what we're showing here. This shows a free body diagram. If I can find my mouse, there it is. This is what they're saying is a free body diagram of BA. Basically what you have to do to find out what these forces are doing to this piece, you have to cut through that bar and find out what the cross-sectional area of that bar is, or whatever shape you're dealing with. And then you can find out what kind of tensile forces it's going to, tensile or compressive forces it's going to be able to withstand. So that's what's going on there. There's your compression. Again, the forces are all being forced in the direction of the piece itself. So it's pushing in on it. Not something that we haven't talked about already. There's that table I was talking about. All they're doing here is rearranging the formula. The formula for stress is stress equals the force over the area. It's that simple. Don't make it hard. Okay, so if you know what the force is and what the cross-sectional area of that piece that you're trying to deal with is, then you can find out what the stress is. Stress signified here by this sigma. Okay. Now you can rearrange it. So this is the analysis for stress, then the analysis for load capacity. You can find out what kind of force is going to be able to be maintained if you know what the stress, the allowable stress is, and what the area is. So you would go and find out allowable stress in some kind of a table. Okay, and I think if we go back, did they give allowable stress on those I-beams and such?
Yeah, I think it does.
Let's see. Yeah, I believe so. Let's see, do we have anything else? Okay, so we'll be dealing with that, and then finally we've got the design for the required, come on, where's my mouse? For the required area. If you want to find out what the area is, then it's the force over the allowable stress. Again, that's just a manipulation of that formula. So this table should help you quite a bit in this chapter, I would think. You know, if you, but you really shouldn't need that if you can do math, for that matter. But it is kind of handy. Maybe you'll want to keep that around. Okay, so now example 9.1, this figure is that example. And note, throughout this chapter, it's basically a bunch of example problems to show you how this, how stress and strain are dealt with and how they relate. Okay, so it says, compute the tensile stress developed in the square steel bar that is 2 by 2, 2 inches by 2 inches in cross section, shown in Figure 9.3. The bar is subjected to an axial tensile load of 95 kips. And then B, determine the tensile stress, and that's the stress and tension, that's what the subscript T is, if the member is a structural steel W8 by 31 beam. Okay, load being the same. So we look at that, and you note that it says it's 2 by 2. So if you cut through that, the area is going to be what? 2 times 2, so 4 square inches. So we know that. We know the load, P if you will, is 95 kips, don't we? So the stress is equal to the force, 95 kips, divided by 4 inches, or square inches, excuse me. If you use your calculator on that, it should come up with something like 23.8. Okay, and what's my units now? Kips per square inch. Right? And note in the book, they abbreviate that KSI. Okay, and they use the lowercase I there. I'm not much of a lowercase kind of guy because I'm mechanical. Har.
So that pressure, P is a pressure.
95 kips.
That is pressure or force?
Force, pressure. Yeah, whatever you want to call it. It's not a pressure like pounds per square inch. No, it's a force. Kips is 1,000 pounds, right?
Yeah.
So yeah, it's not pressure like air pressure or hydraulic pressure or anything like that. It's not that.
We use the first chapter, like chapter 5 or 4, we use kips. That kips and this is same or different?
Yeah, kips is 1,000 pounds. Yeah, you could have said 95,000 pounds there. Okay, this is actually P here is a force.
Yeah,
That's correct. That's a force. This is the area, and then the stress is force divided by area.
stress, that is the density, yeah?
Stress?
Kind of density.
No.
Force per unit area.
Do what?
Force per unit area for pressure. Pressure is a force per unit area, yes, definition of pressure.
We're not talking about pressure. This is stress. Well, this has nothing to do with pressure, like a pressure vessel or anything like that. No. We're talking about tensile stress right now. Okay, then we move on to the next one. We still know that it's the P or the force is 95 kips, right? We don't know the area right now, but we will. And then we're looking for the stress. I'll try to make that a little better this time. So it's force over area. 95 kips. Well, what are we going to do to find the area? Oh, that's what you want me to tell you, right? Go to the back of the book. It tells us it's a W8 by 31, right? Now, if it's like he did in the problems in the last chapter, you could go and look for the W, what was it, 8 by 31? And it probably wouldn't be in there. So we would probably have to change that. 8 by 31, it is in there. And it tells me, it's on page 487 in your book, it tells me that the area in square inches is 9.13. Just so happens that's what the book says. Okay? So on structural shapes like that, they'll have to tell you the area, right? Because you've got all those radii involved on the corners of all your shapes. So you'll have to go there to find that. So
problem is this?
this is example problem 9.1 on page 179.
But it's B.
Yeah, this is part B.
Oh, okay.
This was part A here,
Okay.
and this is part B over here. So 9.13 square inches.
And that's an I-beam, right? The W.
Yeah. This is this particular part we're dealing with here is the I-beam. That would be, I think the 8 would probably be this way, wouldn't it? Eight by 31, was it? So the 8, yeah, the 8 is 8 inches. Oh, I'm sorry, that's the D. So that would be, the 8 is this way.
And then it's the 31 pounds per foot.
Right. Just gonna scratch that out for now. Right, and it's 31 pounds per foot, and then the width is actually given in there. I haven't looked it up, but the area is all I'm concerned about, and the area was 9.13 square inches. You do the math on that one, you should end up with 10.41 kips per square inch. And that's the stress in.
It happens to be 8 too, so you could not scratch.
Oh, really? It's an 8 by 8. Darn it! Should have told me a little sooner. Oh, okay. Let's see. Does that make sense? What kind of? Let's see. We got 4 square inches on the bar, and so the stress is 23.8 kips per square inch, and then on the I-beam, which is quite a bit larger, isn't it? But it's quite a bit larger, but it's only got basically a little over twice the amount of square inches, and it's going to have 10.41 kips per square inch stress involved in it. So, but it's more than twice the area, isn't it? So again, if you're talking about stress, and keep thinking in terms of pounds per square inch. You know, if you've got a flat shoe on, then everything on that shoe, or let's go back to, I think we talked about a waterbed a long time ago, beginning of the semester. The waterbed spreads that weight out over a large area, doesn't it? But if you have a 4-poster bed, it's all going to be concentrated on a small area, those 4 legs of that bed. The 4 legs of that bed have a lot better chance of piercing that floor than that waterbed does. But you're going to have more pounds per square inch on that small area, and there's a case involved right there. You know, 23.8 kips per square inch on that 2x2 as opposed to 10.4. So the more you spread that out, the better off you're going to be. So you're looking for more contact area. In some situations, you can't do that. So then you may have to find a different piece of material that can withstand those stresses. So that's what you're going to be doing, you know, along the way. Jabril? As can you think about what is resistance? The stress? Well, you can in some sense, but then it's not necessarily the resistance. It is in this case, but then later on it's what it can stand. So I don't know if that's a resistance with its ability to resist, I guess. If you already knew what the stress was that the part could withstand, so your ability to withstand a certain stress, then you would have to go and find what kind of forces it would hold up to, and that's what we're going to do in a couple other problems. So it's resistance or ability to resist would be the other thing you want to look at too. So yeah, I mean a force, that's what you're doing with any of these forces, right? Even when we were in equilibrium, you were figuring out, okay, if I've got these forces, what's it going to take to resist that thing moving? So essentially we're doing the same thing. Yeah. Is there another question? Okay, so it's just a matter of figuring out what you've got and what you need, isn't it?
So aren't we just figuring out the basics of where you get that plastic deformation?
Not yet. Nope. Not yet, because you have to deal with stress and strain.
Oh, and strain.
Yeah.
Okay.
So no, we're not. All we're finding out right now is what is the stress in that bar.
In the bar.
Yeah.
From
What
95 pounds.
it's at that certain point with that 95 kips on it, what would that 10S Olsen machine be reading?
Okay.
It would be reading 23.8 kips per square inch. Okay. And then later on, you find out how much can it withstand, okay, depending on what shape you've got and what type of material and all that. So yeah, that's all we figured out right there. At that point in time, at that area and that force, what is the stress in that member? Okay, so that's all we found out. And then, like I said, you can adjust those equations. Maybe we know what the stress is based in the back of the book. We know what the stress is on that particular cross section. How much force can I use? How much force can I put that, up against without having a problem? And that would be, you'd have to go and find P at that point, wouldn't you? Or then later on, you might know what the force is and you might know what the stress is involved, but then you have to decide, okay, so there's a problem coming up here. I don't know if we want to go to that. It's actually on the next page. Well, it's example 9.3. We're going to have some steel rods, and we know what they have to support, i.e. the force, and we know what the tensile strength of that particular material is. Then we have to figure out what the area is to know how big of a rod to go after.